So hello everyone, this is lecture 28 for the quantum mechanics. In the last lecture we were discussing some questions based on the postulates and all we have studied up to here. So I gave you some questions. So let's see the solution. So I gave you this question: the state of a system at t equal to 0 is given and we need to find the time period of the evolution of the state psi 0. So time period will be at which this function will came out to the initial state, that is psi t will be equal to psi 0. So first you need to calculate the psi 0 at psi t, some small t time. Then you just put t there and equalize both of them, and then you will get the t. So let's do the same thing. So we have this. So psi t given at t time will be given by this psi 0. We already know. Just operate this h operator, and h operator with phi 1 will give you e1, with phi 2 will give you e2. So we already know that. So we just operate them, and now we have psi t as this, and we just put t equal to t, and at that time that must be equal to psi 0. So we just compare the coefficients of the eigenstates, that is for the phi 1 and phi 2. So for this 1 upon root 2 and I by root 2, and here we will get this divided by root 2 and this divided by root 2. So this will be equal to this, means both are equal to 1 upon root 2, so we can equate both of them. So that will be psi t equal to psi 0, and we will get this equation. You just can equate them and you will get this equation. From here this will be in the denominator, it will give you e to minus e1 t by h cut equal to 1. Now 1 can be written as exponential plus minus iota 2 pi n. So this will give you cos theta plus I sin theta. So from here you will get only cos theta, and cos 2 pi n will give you 1. So that's how you can write, where n is going from 1 to 3. So you will take only plus here, plus iota 2 pi n. So that will give you 1 here. So we just compare now this with this. So from here you will get capital T as 2 pi h cut divided by e2 minus e1 n, and just h cut will be h upon 2 pi, so it will be h upon e2 minus e1 n. So it will be 1, 2 and 3 h and e2 minus e1. So this will be your time period at which the our wave function will be equal to the initial wave function, that is psi 0. So that's how you can solve. All questions are same. So now let's see one more question. This was this. So psi 0 was given. We need to find the time at which psi t is orthogonal to psi 0. So to make them orthogonal, we know that their inner product should be 0. So let's take the inner product. First we need to find the psi t, and psi 0 is given, so we need to find psi t. Then we will just dot product them. So psi t will be given by, we just use the same formula, this one. So this will give us this your wave function at particular time, and now we will just take the inner product, that is psi t and psi 0 must give you 0, or psi 0 psi t must give you 0. So both conditions should satisfy to make this orthogonal. Now we will just solve them, and again you will get, means this will act like 2 I cap 2 j cap, and this is 3 I cap 3 j cap. So it is just like your I cap and j cap basis vectors. You have the initial wave function, and you have the at any time. So this is your just dot product. So this multiply this, and this multiply with this phi 2. This will give you your dot product. So that's how you can equate, and you will get this equation. From here again we will get minus 1, and we can write as plus iota 2n plus 1 pi. This time we have write 2n plus 1 because we need to get 1 here, minus 1 here. So at n equal to 0 you will get pi, so cos pi will be minus 1, and n equal to 2 you will get 5. So all terms will be odd, and you will get minus 1. So now we will compare them, and again we will get the t as this. So it will be this. So this is your time period at which this psi t will be orthogonal to the psi 0. So that's how you can solve. So in any question, if you are getting any doubt, you can just put in the comment section. I will make a separate solution, complete solution for that question. So I'm just discussing them fastly, because I know you already know these things. We are applying same thing in all the questions. Still you have any doubt, so you can just put in the comment section. I will make a separate video for that particular question. So again we have this question, so we can solve this also. Consider a system whose initial state psi 0 and Hamiltonian are given by these, and we need to find the energy carried out and what values would be obtained with that probability. So with what probability? So again this Hamiltonian operator is given, so we just need to find the eigen values. So we'll get the what energy eigen values we will get. So this operator will give us the energy eigen values, and to find the psi 0 in terms of the basis vectors, we need to find the basis vectors also. Just we have the eigen values, we can find basis vectors also, and we have, when we have the basis vectors psi 1 phi 1 phi 2 phi 3, then we will just take the inner product with the psi 0 to get the c1 c2 c3, and after solving that we will get this, means eigen values will be minus 5 3 and 5, and phi 1 phi 2 phi 3 will be this, and this psi 0 can be written in this form: c1 phi 1 c2 phi 2 c3 phi 0. Still we don't know c1 c2 c3, so we can find them just using this formula. Phi 1 psi 0 will give you c1, and phi 2 psi 0 will give you c2, and same c3. So you will get C1, C2, C3. Now you have phi 1, phi 2, phi 3. You have C1, C2, C3. So you can write your wave function, initial wave function. And now you can find this psi at any time also. So that's how that using the same formula, this one, you can write. And you have psi 0, you will just operate for h cut means h cap operating will give you E1, and h cap operating on the phi 2 will give you E2. So all eigenvalues you already have, and you have the coefficients. So you can write your wave function at particular time also. And when you get three matrix there with the with the eigenstates, you will get 3 column vectors. So you can just add them and you will get your at any time matrix also. So you can write your wave function in terms of matrix also at particular time. So you can solve this. So add one more part in this, that find the probability of the system at time t in the state psi 0. So we need to find the probability of this at any particular time. So probability at time will be given by this psi 0 and psi t, the average expectation value, means just inner product of these two, and the square of that mod square will give you your probability at any time for this function at time t. So I hope it is clear to you. Still having any doubt, just put in the comment section. I will resolve that. So today we will study a new topic, that is equation of motion and the Ehrenfest theorem. So let's see what we will study here. So up to here we studied that when we find the eigenvalues or the expectation values for the energy, so they will remain same with the time. But it's not always the case. Sometimes they change with the time. So that's what we will study in the Ehrenfest theorem, that expectation value change with time. So only those operators which commute with the Hamiltonian, they give the same eigenvalue, same expectation value with time. But those who don't commute with the Hamiltonian, so those values will change with the time. We will see in this that how they will change. So in this we will study that how our expectation value evolve with time. So expectation value of any operator A is given by psi A psi and divided by psi psi. So this is a general formula, but in general case we have this as equal to 1. So when the wave function is normalized, so this will be 1. So it will be given by simply this formula. And now the psi can be written as C1 phi 1, C2 phi 2, and average expectation value of energy given by E1 P Y. So you must know how to find the expectation value in terms of the probability. I already discussed these things. So let's see the time evolution of this operator A. So for that we need to derivate this with respect to time, that how it is changing with time. So and this A is equal to this. So we need to differentiate this complete. So let's say this still we are assuming that this operator is depending on time. So it is time dependent operator. So this is psi t, at and psi t. So we need to differentiate them. So we'll use the product rule. So first we will take this as first function, this is the second function. Then we will just take the dot product, means the differentiation of this. So this will give you these 3 terms. So we just use the product rule here, nothing else. Now see, this is dA by dt. This is how the operator is evolving with time. So we need to simplify this equation. So let's see how can you simplify. We know from the Schrodinger's equation that this is how the Schrodinger's time dependent equation written as. So d psi t by dt equal to 1 upon I h cut h psi t. So this is how your Schrodinger equation is time dependent. And see, this Hamiltonian operator is Hermitian, so h dagger is equal to h. So we'll just take the complex conjugate of this complete equation, that will give you this cat will change to bra, and here also this cat changes to bra, and it will be h cap. So h dagger will be give you h again, so that's how we written as h, and I will give you minus I. So this is your conjugate equation. Now we will use this equation and this equation here. So here we will use this term, and here d by dt and psi t we will use this. So we will just substitute these two terms in this equation, and we will write first this and second this and third this. So in these two we will take some common things. So after simplifying you will get this equation, 1 upon I h cut we will take the common, and you will get this plus this third term is as it is. Now see, here we will get this a h cap minus h cap a. So this is nothing but commutation of a and h. So we can write this as commutation ah, and this psi t plus this equation as it is. Now see what this represents. This represents the expectation value, means whatever inside, this is represent the expectation value of that value. So we can write this complete as expectation value of ah, and this is the expectation value of dLA by del t. So this is dA by dt equal to this, and this is all equal to this. So this is our equation now. This is called the equation of motion in quantum mechanics. So you must remember the equation of motion. We will use it in the questions. So must remember this. Now we can see some things. We assume that this operator is time dependent, but let's see if this operator is not depending on time, then this will give you 0. then this equation will reduce to dA by dt equal to 1 upon I h cut ah in the commutation. Now see, if the operator commutes with h, then this will give you 0, and this will give you 0, then this must be equal to 0, and from here we can see that this must remain constant. So this is the expectation value of a operator, which will remain constant. So that's how we derive the result, that if any operator will commute with h, then expectation value of that operator will remain constant. As we already know that means Hamiltonian operator, energy operator, that expectation value always remains same. Energy operator, we already seen the examples. So because h operating with h will always, means h will always commute with h, so that's why the means expectation value of h will always remain same. Energy expectation value remains same with time. So we already seen the examples also that energy expectation values didn't change with time. So that's how we get those results. So any operator which is commuting with the h, those expectation value will remain same. So must remember these results, very important results, and this equation of motion. Now let's see the Ehrenfest equations. And same like Hamiltonian, you have angular momentum also commute with h, and L square also commute with h, so they will also remain constant. So to see the Ehrenfest equations, first we need to remember this equation. We are assuming that a is time independent, that's why del a by del t term is 0. So this is your equation of motion. Now in place of a, we will have the position and the momentum operator, then we will call whatever equation we will get as Ehrenfest equations. So must remember, we will operate this equation with the position and the momentum operator. So when operator a is either the position or the linear momentum operator, then the resulting equations are called the Ehrenfest theorems or the equations. So first let's assume the a operator as the position operator. So dy dt of x will be equal to 1 upon I h cut x and h. So now Hamiltonian is given by p square by 2m plus v. This is potential energy and the kinetic energy term. So the operators. So in place of h we will write this, and let's find the commutation. So x will commute with x p square by 2m and x vx. Now see, this will give you 0 because we studied in the commutation that any second term is function of x. So this will give you 0, and from here we will get 2I h cut p. So you must remember from the commutation lecture. So how we will get this? So this will be equal to this. Now see, this 2 will cancel out and you will get I h cut p by m. So we will just substitute in this equation the ah. In place of this we will write this. So this will get, you will get I h cut p by m and 1 upon I h cut. Now these terms are constant, so I h cut will came out and cancel out. So it will only remain as p by m. So this equation is called the Ehrenfest equation for the position, dx by dt equal to p by m. So remember this equation, we will use this in the questions. So this is the first equation. Now to find the second, so a is equal to p. Now we will assume operator a as linear momentum operator. So p, let's find the commutation of p with h. So p and h is p square by 2m plus vx. So this first p with p square will give you 0, and p with vx what it will give. So p operator is nothing but minus I h cut del by del x. So del by del x will directly operate on the second function, that's we know from the property of commutation. So this will be equal to minus I h cut del v by del x. So this will be equal to this. So substitute in the equation, this equation. In a we will write p, so it will be minus del vx, means this is I h cut, so I h cut will cancel with this I h cut. So we'll get minus del vx by del x. So Ehrenfest equation for the momentum, this is called the Ehrenfest equation for the momentum, and this is our second equation. Now see, we can see this in the other way also. Now let's find the differentiation of this with respect to time. Take the second order derivative, it will give you d square x by dt square equal to d by dt of this 1 upon m dy dt of p, and see, m take here m this side, and this will be like this. Now you can see this equation, this is something like force, means this is m, and this is something like acceleration, equal to this is potential energy differentiation, means the gradient of v, and gradient of v is defined as force. So we can write this equation in this term, f equal to minus del v, and we can just find the analogy between them. But see, this is not actually force. So in the quantum mechanics there is nothing something like force, because here we have the expectation values. So this is not some force and that thing. So you must remember the difference between them. So here, as here also we can see that this is dp by dt equal to force. So this is nothing like rate of change of momentum. So this is because the expectation value. So you must remember the difference, and this is how and why we are calling them the equation of motion and all that. So that's the reason behind. So must remember these equations, very important for the questions and the exam point of view. So I think that's all for today. In the next lecture we will start the applications of the quantum mechanics. So here our half quantum mechanics is completed. So we'll meet you in the next lecture. Thank you everyone.